Good morning. Thank you for making it to the session that late in the conference and that early in the morning. Thank you very much to organizers for, first of all, for inviting me. Secondly, for absolutely wonderful workshop. I enjoyed literally every minute and every talk here. So it's a session about materials. I'm going to give you a roadmap about materials for quantum spin and topology based materials, but not only. So I felt that I need to go slightly broader. So my main focus would be materials with spin and topological properties. My talk would be somewhat different from what we heard up to now. It wouldn't be no mass at all, but it will be budget, markets, expectations. I'll try to give you a point of view of the end users of technology, what is needed from a materials point of sight. And it kind of combines my current interest of material scientist and also development sustainable businesses from quantum technologies. So it's an overview. It's not a detailed talk. In a way, it's easier today because we heard in details about many materials platforms in last few days, and you should have a great knowledge already, better than me probably in some aspects. So I'll focus, as I said, on spin and topology, and I'll focus on quantum computing, though I'll be talking about other aspects of quantum applications as well. And I will talk about reasonably well-established material systems and emerging ones. And a special compliment to this place, which is completely serene and idyllic. Otherwise, I think it's my typical avatar of myself, but for the sake of time, let's move on. It's a tutorial, so maybe for some of you, it will be useful to have a look at roadmaps, review articles, which I used for preparation of this talk. It will be much more than this, but I would like to recommend it as a list of literature for home reading if you're interested. And they're covering really very broad range of materials today. When we're talking about quantum market and quantum industries, at least in those aspects where we rely on materials, there are three main directions: quantum computing, which is main focus of today, quantum communication, and quantum sensing. Defining what they aim to do. Quantum computing is kind of easy. Function of these quantum bits to perform computation. Communication, cryptography, quantum key distribution, also quite defined. Sensors, I couldn't find a good definition. This one really not quite satisfactory. It's to be better than classical sensing and to sense impossible. Yeah, true, but kind of not very precise definition. Anyway, where we are. Why materials? Why materials are important for quantum technology? In February this year, Kureka published this overview of investment. So up to now, up to February at least, only public investment into quantum technology was almost $45 billion. Quite impressive. And we probably would never know how much private sector invested into it. That's how it is distributed across the world, if you're interested. It's investment. Now we're moving towards market expectations. And this report is not very modern. It's 2 years ago, almost 2 years ago, from McKinsey. They expect that all this investment will generate 106 billion of quantum technology outputs. In principle, it's not that great return, 45 versus 106. It's factor 2.5, not a huge difference. So yeah, and it will be, I think, it should be some year, something like 2040. There is also another report from a couple of weeks ago It's Oxford Economics report, and they predict, well, a bit later in 2050, but significantly larger number, 285 billion, and only in the UK. So it's much, much more optimistic report. It's a prediction. What we trust, one figure, another, or a third figure, it's a bit difficult to say. It's a prediction. And nevertheless, McKinsey report is very, very detailed. And again, if you have an interest, I do recommend to look at this second reference here. This report outlines that out of all return investment, almost 90% will be into quantum computing. And it's only direct outcome. It doesn't count, well, in this number, it doesn't count secondary markets such as pharmaceutical, finances, automotive, which will be significantly larger. Okay, we'll keep it in mind. Out of all investments up to now, out of those 45 billion, almost 80% went to equipment, component, and hardware. So all of them, equipment, component, hardware, they're material-based. So majority, vast majority of current investment and vast majority of expectations would be one way or another related to the material successes. If to look at different investment into different material technology platforms, majority goes to superconductors, photonic networks, a little bit to spin qubits, trapped ions, kind of slightly secondary. It's of course ions, it's not material technology, but infrastructure around trapped ions is very significant and also material related. Right, today I'll be talking about these main material platforms. That it's not everything, but we don't have much time. So well developed, and it's a degree of development, superconductors, semiconductors, wide bandgap materials, emerging, and it's also kind of degree of emergency, topological and skyrmionic materials. How it looks more in terms of device, current device implementations, superconductors, for example, IBM qubit processor, I'll be talking quite a bit about it. Semiconductors, various quantum dots, again, variety of implementations, there's one gate-defined or gate-controlled quantum dots, color center and diamond. Superconductor, semiconductor heterostructure, nanowire for topological representation, again, one of possible solutions, and skyrmionic device, cubic device. You can note that it's only one here is a cartoon, the rest is already physical implementation of different degree of maturity. This one, as far as I know, is in process. I will try to give you the latest numbers and latest developments I could find. I can't guarantee they are really the latest. The world is so fast developing that you might see better results than I found. Please let me know. I would be really grateful. Qubit. Very simple, very basic. It's a tutorial. In classic world, we have 0 and 1. They're completely separated, either 0 or 1. In quantum physics, a qubit is a superposition of 0 and 1, and popularly people saying it can be both in both states simultaneously. It's not a very correct cartoon. I think block sphere is the best representation of a qubit. So it can be everywhere along the sphere. Fine. Metrics for qubits for quantum computing. There is plenty of parameters, and sometimes people use them not very accurately, at least not very consistently one to another. I would say we can focus on two main here, coherence time. It's a time interval when information is stored and not forgotten. I like very much this cartoon quantum phase coherence, I remember over a period of time, and decoherence correspondingly, I forgot. So it's changed, it's a period of time when qubit forgets its phase. And another very important one is fidelity. It's how closely operation of qubit is related to its ideal operation. And people typically speak about single qubit fidelity or 2 qubits fidelity. I will start from superconductors. Then, well, I can say classic superconductors, quantum superconductors, of course. They are not spin or topology based in a direct sense, but it's such a well-developed technology that it will be our benchmarking for all other materials. Standard qubit in superconducting qubit, it's a Josephson junction. Typically two superconductors divided by an insulator. Historically, niobium oxide, niobium. There is current through this structure. Phase of the current, we have copper pairs here with certain phase. When they're tunneling through insulators, through the tunneling junctions, they change their phase. It's a historical phase qubit. It's not used much nowadays, but it's still very valid, very clear physical picture what's going on. The circuit is, electrical circuit here is LCR circuit. It's an inductor. It's also a capacitor because we have tunneling barrier. It has, and as a result, it's an harmonic oscillator. It has two defined 0 and 1 states, which are defined by current through it, and physical state can tunnel between them. All is nice, all is simple and clear. Physical interpretation, in this case, it's a planar structure, can be like this. Again, one of the first one, planar transmon qubit. It's a very busy slide, and I'll try to come towards material issues with superconductors here. Josephson junction-based structure can be in multiple geometries: transmon, xmon, fluxonion, shunted flux qubit, gate mon, so it's plenty more. In terms of current successes, the largest number of qubit, coherently coupled qubit, 1,121 from IBM. I will come to this. It's the largest number. It's not the best quantum computing chip, though. Nevertheless, it exists, the chip called Condor, released by IBM in December 23. It's not the largest quantum computer yet now. Slightly bigger number was demonstrated last year by atom computing based on cold atoms. The best results in terms of parameters, MIT earlier this year demonstrated single qubit fidelity 99.9998, couldn't find anything better, and 2 qubit fidelity from IQM 99.9. Again, I'm pretty sure those two are record numbers. Materials platform, as I said previously, it was primarily niobium. Nowadays, it's mainly aluminum oxide junctions, very easy to fabricate, good performance. Other materials coming up, mainly titanium nitride, titanium niobium nitride, and so on and so forth. Important here, the state of the substrate. Substrates typically either sapphire or very highly resistive silicon, so it's low losses substrates. It's all nice, clear, established. Where is the trick? Trick is in defects. Defects, I'll be talking today primarily very trivial defects. Let's have a look. In amorphous oxide barrier of the Josephson junctions, it's amorphous oxide, I should stress. they're low-level system. So they're TLSs, which are absolutely parasitic and detrimental for the qubit performance. Decoherence, losses, it's probably the main thing happening here. In terms of superconducting material itself, it's quasi-particle tunneling through the Josephson junction, dephasing, disturbing the best performance, expected performance of the system, uncontrollable. Then surfaces. Dissipation at interfaces and surfaces is enormous, and it's essentially surfaces is an enemy of a qubit, of any qubit, essentially. And surface spins and fluxes and kind of flux-related noise. Let's maybe look at it into more detail. If we check inside of our aluminum oxide barrier, it's amorphous. There is no order by definition. Atoms can tunnel back and forth. We have hydrogen impurity. They create some kind of spin rotation, charges, so it's pretty unpleasant. And we have trapped electrons, again, primarily at interfaces with aluminum. So we have no electrical noise there. Externally, kind of looking outside of our device, adsorbates, still hydrogen, but outside, oxygen. What else? We have resist residue, which is organic mass. We have structural damage to the substrate and contamination, atmospheric contaminations, which will be sitting there. It looks like nothing major, right? It's a bit of oxygen, a bit of hydrogen, some strange vibrating atoms inside of aluminum oxide. Effect of this is severely detrimental. I was talking about IBM and the Condor platform they created. So it's kind of a roadmap I've made out of their progress. It started reasonably recently as a full device. In 21, they call their chips by names of birds due to some reason. Eagle, 127 qubits. Very quickly progressing to Osprey and to the Condor with more than 1,000. But at the same time, slightly after they released Condor, they dropped number of qubits almost 10 times. The reason, Condor was so lossy, so poorly performing, they couldn't increase number of qubits any longer. And that, I'm not saying it's the only material issue, but material performance is one of significant bottlenecks. So it's getting larger, and they couldn't maintain scalability of materials and high quality of materials at the same time. What's the company done? Instead of... Yeah.
When you say 1,000 qubits, can one actually create an entangled state involving so many qubits at once?
Yes, as I say, they could, yeah. So they're not just array of qubits, they're functional qubits, but they're very low, they're entangled, but they're very lossy at the same time. So they went along completely different paths. They decreased number of qubits. They created gates. So there are 133 qubits, but they're gated. So in reality, it's equivalent of multiple by 3 number of qubits. Heron showed record low losses. It performs much better, but this improvement in the performance, it's not through solving material issues. It's through creating quite complex computing architecture about it. They expect this year to release Flamingo and some more steps further on. And finally, in 33 or after, they plan to release Blue Jay, which will be 2,000 physical qubits with gates, with 1 billion of gates. they say only Blue Jay will achieve full computing power. Here we are. I should say that while they released new chip every December 21 to 23, it was nothing in 24, and 25 we'll see what happens in December. Saying this, I found just last week this paper which fascinated me quite a lot. So IBM released financial milestone. So last week, the sales from their quantum computing reached $1 billion. So whatever system it is, how imperfect it is, it's already a commercial product which brings money. I almost won't be talking about our own research, but that's one of few exceptions here. It's how people study defects in superconductors. So we have superconducting resonator, niobium nitride, and we studied quite unusual TLS system here. It's not very visible here, but we measure frequency versus time, essentially. And we have two TLSs. One is and we change temperature, 310 millikelvin. So one TLS is very stable, at the same, very narrow, at the same frequency. Another TLS changes its frequency here and there, but still more or less stable and narrow. Another one appearing very suddenly, and very broad one here. So it's a vertical line of a broad, strange TLS, which we couldn't identify what really it is, but it's very coherent, very high coherence, nonlinear density of state, strange dependence on magnetic field, and very big effect on the system. Right? They're appearing suddenly, they're not controllable, they're unpredictable. What to do with them, it's up to us as material scientists trying to find solutions. Right, now I finished with superconductors. I'm going to talk about spin and topology. And the next big topic, and in terms of maturity and research invested into it, spins and semiconductors. Three main systems in terms of spin qubits. Gate-defined or gate-controlled quantum dots, typically either in silicon or in 3-5 systems. Donor spins or shallow dopants. Typical system is phosphorus in silicon. And color center or defects in band gap materials. I think the correct, physically correct definition, optically controlled defects here. Interestingly, in terms of size, if we have our Josephson junctions somewhere here, almost millimeter, high microns, then we have topological devices and trapped ions above 1 micron. Gate-controlled semiconductors would be here, less than 100 nanometers. Self-assembled dots, 10 nanometer and a bit more. And finally, the smallest would be our NV center, color centers, just a few nanometers. In terms of applications, shallow dopants, gate-controlled ones, they're used primarily for computing. NV centers are best used for quantum sensing and quantum networks. Again, historically, majority of gate-defined spin qubits been done out of 3-5 systems. Advances here, very simple conductance band value, very nice energy structure, and small effective mass of electrons. Cons here, non-zero nuclear spin for many atoms in the system, leading to hyperfine interactions, and leading to decoherence. Almost all people now moved to a silicon-based system, which is silicon, germanium, variety of silicon, germanium, core shell structure, or interfaces or alloys. low nuclear spin, even in untreated silicon, we have only 5% or less of silicon-29, and it's the only isotope with nuclear spin, and which can be significantly improved by silicon enrichment. It's quite established technique. So we have weak spin-orbital interaction. As a result, we have a long coherence time, which is record long. SIM is compatible, but on the other hand, on the negative, for each positive, always there is a negative, large effective mass of electrons, complicated energy band, leading to low leaking states, which is difficult to deal with. And despite all research in the semiconductor and the CMOS technology, there is still scalability and reproducibility issues. Now, shallow dopants. Again, phosphor and silicon, substitutional atom. It has an additional electron, so it gives a negative charge. Importantly, it also produces a spin to silicon. Talking about enriched silicon, when normal silicon, 20 natural silicon, will look like this, slightly messy. It will have 28, 29 with a spin, and silicon 30. With enrichment, you can have this almost ideal structure. And in principle, it's enough to do 100 or so nanometers of enriched silicon to significantly improve performance of our isotopes there. For redoubt, people using single electron transistors typically. It's exceptionally beautiful STM image of such device, single donor spin qubit. And you can see, for instance, that individual phosphorus atoms are placed here, and the whole infrastructure for control and measurements patterned around it. Difficult work, absolutely fantastic, beautiful results out of it. Right, problems. I've more or less defined main material systems here. I should probably say, importantly, it's long coherence time. Good milliseconds, maybe about 100 milliseconds now I've seen, so it exists. What is the problem? Problem is still nuclear spin is substrate is not treated. Within structure itself, we have semiconductor insulator, various interfaces, charge traps within these interfaces, and in devices, potential fluctuation of spins, of electrostatic fields, and again, surface inhomogeneity, almost impossible to do anything, provides lots of electrostatic defects, and it provides also strains. And single spins in particular would be very sensitive to strain, to mechanics here. Third and last class here, color centers. Typically, people are talking about NV centers in diamond. It's the most studied structure, classical structure, very nice. It's NV center. It's substitutional nitrogen atom and a vacancy. They have double bonds. They have negative charge. When we're talking about NV center, we're talking typically about an NV minus center, though there are plenty of others. Advantage here is very clear, very simple, very robust energy diagram. So we have ground state, spin triplet ground state. We have excited state, and to transfer this center from ground to excited state, I use green laser, very common one, 515, and we use 532, typically works perfectly well. We are at excited state, then system relaxes back down. It relaxes through two intermediate singlets, and it produces fluorescent light 637 nanometers. It's an ideal case, and 637 is so-called zero phonon line. In reality, this center produces quite a broad band of wavelengths. And this important 637 line is there, but it's kind of obscured. It's not huge intensity, and it's rather masked by other emissions. It's also large spectral diffusion, and it's not compatible with telecoms, which would be good to have. On the positive side, it's at room temperature. It's nothing simpler than that. It's room temperature mechanism. It's biocompatible, and lots of work on use of nanodiamonds in particular for quantum bio applications now. And it's photostable, up to some degree, but it's photostable. Looking into materials aspects of this, primarily diamond, but silicon carbide is getting more and more popular now. Defects are mainly NV centers, but in principle, it's a whole zoo of defects. Slightly messier, but they have pros and cons. It's silicon vacancy, it's V center, D vacancy, they're really plenty. State of the art, T2 minutes, up to the minutes at room temperature. And it's low spin orbital coupling, which is again always a plus. On the negative side, it's quite susceptible to electrostatic fields around, and diamond is, well, it's difficult to surface control it. So I see now, in terms of literature, so much work on diamond is related to surface functionalization and improvement of properties that it's much more than in improving physics of diamonds. So it's all about chemistry, surface chemistry. Where noise comes here. Latest defects. First of all, you're lucky if you have one NV center. Typically, you have many, and they would be pointing in different directions with their moment, and they will be interfering, nothing good. But also other dopants. It can be carbon, typically, and it's good when it's carbon-12, but notoriously, it can be carbon-13 with nuclear spin, and we are coming back to the flux, noise, and decoherence on spins. We have both at the interface and in the bulk, we have dangling bonds, nuclear spins, and electron traps. Again, nothing particularly new compared to, let's say, other semiconductors or to superconductors. The same classes of naughty, uncontrollable, very simple defects. Surface roughness, surprisingly, diamond can be quite rough, and extended defects in bulk mainly. But what they do, they create strains, and NV center is very sensitive to internal nanometer atomic scale strains and distortions. Challenges, summarizing all semiconductor story, challenges here is deterministic fabrication. In particular, kind of gate controls are all right when we lithographically create quantum dots, but trying to put an NV center in the right place or a single atom in the right place, it's quite a challenge. And imagine if you talk about computing or networking, you need not a single atom, you need an array of atoms in the right place. So they're put in the right place and they communicate. So it's unsolved, more or less, challenge now. It's noise. Noise is always connectivity. We need not only to place, but let them talking appropriately, control and read out. There is quite a bit of progress, though, in terms of already existing applications. Computing of various types, I've covered it more or less, but also sensing, primarily with NV centers. And again, due to its temperature robustness primarily in biofield, but also quantum internet or quantum networking. And I would like to show this paper published in late 24. It was quite a famous example. So in the Netherlands, they placed two single spin diamond qubits, one in Delft and other in the Hague. So distance between them is 10 kilometers, but they used a midpoint, so it's overall 25-kilometer distance. And those two spin qubits, they started to talk. So it was so-called heralded entanglement demonstrated, which I think it's pretty cool, and it's one of the best examples what can be done with spin qubits so far outside of computing. Summarize.
So is this? It looks like it's over commercial fiber because it's in the figure.
It's a commercial. It's a fiber.
So
yeah.
they just use the commercial fiber.
Yeah, but they showed that they can be entangled. Yeah, 25 kilometers of fiber. Yeah, I think it's pretty commercial fiber. Yeah. Right. Summarizing, it's not the newest table, so it's from this paper. What is good, as I mentioned a few times, coherence time is definitely good for all classes of semiconducting spins. Milliseconds, seconds achieved straightforwardly. Number of qubits, 7 qubits were demonstrated for gate-controlled quantum dots, and 4 qubits, as far as I know, were demonstrated recently for qubits, meaning connected phased qubits, been demonstrated for NV centers. Sounds like a great outcome, but remember 1,000 at IBM, superconducting one, so it's a long way to go. I would say importantly is to pay attention to sensing properties. Spin qubits can be used for magnetic field sensitivity, and it's low picotesla per square root of hertz. And they can be used, NV centers specifically used for thermal sensitivity and for electrical field sensitivity. So for me, it looks like probably a better defined future for spin defects in semiconductors. Right. Now, from more or less established platform, I'm going to emerging one, which would be topological materials and magnetic skyrmions. And again, my task is easy. Quite a lot have been already told about these two systems in last couple of days. And specifically about topological systems, I'll be talking quite a bit about controversy of what we know nowadays about them. I don't want to offend anybody, and if you know better, please do shout. So, but it's an interesting state of hyper and uncertainty in the community about topological qubits. So, topological materials, we all know they're insulating in bulk, they're conducting in the surface. If it's a 3D material, we have conducting surfaces. And I should say, they exist. There is absolutely no doubts. They exist. They've been demonstrated 100, if not 1,000 times. In 3D, it's conducting surface. In 2D, it's conductive perimeter of material. In 1D, there are boundary charges at the end of nanowire, typical structure. In terms of energy, I think it's pretty cool. We have insulator. If we would have standard insulator, we have conduction band, we have valence band separated. In topological insulator, we have all these surface states, 2 green lines here. In a real ARPIS experiment for bismuth selenide, we can see this conduction band, we can see this valence band, but we also have this red lines of surface states. Absolutely beautiful. From well-established topological insulator, I'm moving to Majorana zero modes, and it's much more controversy here. They've been predicted in particle physics in 1937, 100 years ago almost. They're zero energy, they can exist, they could exist without any excitation. They are their own antiparticles, well, non-abelian anion behavior predicted. They're topologically protected. They would be ideal for topological computing, of course. Braiding, robustness, all these things. Has it been demonstrated? I'm not sure. So I'm summarizing. I'm not the biggest expert in topology. I'm summarizing what I read and what are other people saying. Topological qubits been studied quite intensely. I think it's a very big belief of Microsoft in this technology. Quite a lot of works funded directly or indirectly by Microsoft. Huge interest. Material systems which were used, quite a variety of them, and there are probably a few more I am not using here. Typically, it would be semiconductor, superconductor, topological insulator, superconductor. So superconductors are almost always there in one or another role. It can be ferromagnetically doped superconductors, it can be superconductor skyrmions, and so on and so forth. Experimental evidence of MZMs in such systems and experimental evidence of topological qubit, working topological qubit is still under debate. Their non-abelian character, again, as far as I know, hasn't been proven. It's been a very interesting work. I think everybody knows it was a bit of scientific cliche, not in a good sense, unfortunately, published in 2018. So indium antimonide nanowire on superconductor substrate. Signature of MZMs, they claimed, is appearance of this plateau in reasonably large magnetic fields, and also this differential conductance, peak at 0 voltage. It was associated with MZMs. While no one argued with the results, with experimental observations, a main argument that it can't be directly or unambiguously associated with MZMs. So paper was retracted 3 years later, and though now there is still research in this area, and as I've seen a couple of articles where similar signatures being reproduced, the question is still open if it can be absolutely attributed to MZMs. We already seen it yesterday. Microsoft Majorana 1 chip released in February this year. February was very rich for various announcements. Community criticism was quite broad. My understanding, first of all, because of scarcity of details which the company announced behind this release. Interesting observation. So the research, Microsoft research was funded by DARPA, and DARPA now in April, the funding agency invited, on one hand, 10 established technologies for quantum computing for benchmarking. And benchmarking essentially when you bring a number of platforms, it can be not necessarily quantum computing, 10 devices which claim they do a certain function, and you compare them on the same task, right? So they invited 10 established quantum computing technologies for benchmarking, and separately they invited, they called it underexplored technology, where Majorana 1 is one of the technologies, and another one is quantum psi on it's a photonic chip. So it was in April. I haven't heard since then, and I don't know what is the timeline, but I presume somewhere within next few months, maybe a year, they will release results of this double benchmarking for established technologies and more emerging technologies. So let's keep an eye. It probably will be some answer towards this. So topology for quantum computing is still under debate. I would like to finish here on a positive example, quantum standards. And here's the work which we done with Torsten last year. Topological materials, specifically magnetically doped topological materials, are absolutely ideal for realization of quantum ampere. And it's a combination of quantum Hall effect and quantum anomalous Hall effect. When we measure device like this, we have clearly plotted Landau level in magnetic field, and we have disappearance of longitudinal conductance, so absolutely classical signatures which allows to realize quantum ampere and in proximity through Kibble balance, quantum kilogram can be done. So quantum ampere is almost done. Quantum kilogram and quantum candela through cryogenic radiometry, it's in progress. And to be honest, I don't know how much progress there, but in principle, out of 7 SI units, 3 can be done through topological insulators. Skyrmions, last system, and I would be really brief about it. Well, many people in this audience authored this paper, and I can just show a few slides acknowledging your great work. For me, the beauty of skyrmions is ability to work in classic and in quantum regime, and strictly speaking, its ability to perform in classic, neuromorphic, and quantum regime. So 3 very different approach to realizing computer can be done through skyrmionic system. As far as I know, it's the only system which potentially allows this flexibility. Though it's, of course, it's still quite in the beginning of the journey. Interestingly, skyrmions are so robust. They exist in bulk crystals, in multi-layers, and here a long list of materials where they've been observed in terms of electrical properties. They are mainly metals and insulators, but they exist in some semiconductors. Zelashinsky-Maury interaction, frustration or KKI. They can be observed by a variety of techniques, neutron scattering, Lorentz, MFM. Interestingly, in van der Waals ferromagnets, very cool topic now. People also study them with great energy nowadays. Quantum side of skyrmions, quantum deepening, quantum helicity tunneling, and quantum nucleation. All of this can be used. At the moment, the best concept of, it's not skyrmion, it's Meron device, proposed by Christina and Christos here as 2 Merons insulating layer tunneling, so not far away from Josephson junctions in terms of the concept. Right? It can be controlled by strain, magnetic field in plane, or electrical field out of plane. Theoretically, number of platforms have been proposed for skyrmionic quantum devices: gate quantum computing, quantum memory, topological quantum information platforms, various logic elements. I've counted 3 or 4 recently, and quantum neuromorphic computing, which, if you ask me what it is, I don't know. I can't explain it. but it's a mere list of what I've seen. So we tried to, with colleagues, and I can refer to this nice QR code if you're interested, paper on archive. We tried to summarize the best what can be done, what was demonstrated for spin and topology-based system right now, and it's in present. And I didn't cover in this talk spins and superconductors and 2D materials, which would make it even longer. But nevertheless, in terms of operation temperature, in terms of coupled qubits, again, the max number 2 to 7, not that great up to now, but good coherences time, quite good temperatures. Readout is really flexible, can be electrical, can be optical. For emerging systems such as magnetic skyrmions and topological, they're mainly in the concept stage here, and we also summarized benefits and drawbacks of each technology. Again, if you're interested, please do have a look. And next, my last slide really is where it's all will be going and what is the future for spin and topology materials. And I tried to kind of put it through my talk. At least for now, it doesn't look like mainstream quantum computing, it's where it's all going. Superconductors are doing so good and so much effort and money already invested there that to cover that field is really how to, more or less similar is proposing something completely different to silicon CMOS. Yes, it would be advantages. Yes, there are certain parameters much better than currently demonstrated, but it will be certain niches. And I think it's important for us to realize this important niches where spin and topological systems behave the best and work on strengths. And doing material research, trying to remove all obstacles and barriers. For instance, here we talk about magnetometry, so magnetic sensing. We talk about temperature and pressure sensing with spin superconductors. It can be superconducting circuits, spins in superconductors for readout and control, as circuits for readout and control, low losses again, proposed in such systems. Topological states, if they exist, they will provide robustness. And of course, skyrmions, as I mentioned, it's their versatility and being able to work in classic, neuromorphic, and quantum regimes. So if you want a system which, let's say, gradually develops itself and can perform in different environments, then it may be skyrmionic one, being completely flexible and agile. So my conclusion, spin and topology, not the most developed platform, but they have their pros and cons, and we need to work on it, on pros. Future for scalable computing, it should be as scalable as possible and working in as relaxed an environment as possible. And by relaxed, I mean low field, higher temperature, sustainability to noises of all kinds. Major materials challenges, defects, disorder, decoherence, and scalability. So scalability, I mean, if you don't have a defect on a small chip, it's not necessarily that you won't have it in a large chip. I would like to finish this. It's Amazon, everybody knows. Marketplace, if you don't know, they have Amazon Bracket. You can just Google it. In Amazon Bracket, you can find quantum computers. So Amazon sells quantum computing time from 4 companies. IonQ, it's trapped ions. IQM and Rigetti superconductor technology, and QERA neutral atoms. So you can buy time out of these 4 companies, and they say that these purchases were used for solving these completely different types of issues by their customers. And again, I've already showed it, but I'm so fascinated, I keep it again. IBM already earned 1 billion this month for selling their quantum computing time. So where physics meets business needs, it's probably the most interesting and most applied story of all my today presentation. What I'm trying to say, it's not future. It's now. It's happening, and it's up to us to make it happening more beautifully, more physically robust, and more reliable. That's it. Thank you.